Hi there, Turgeon here, bringing you physics from afar. This is a system tension problem. It's really about the system, but the difficulty most students have is figuring out how to get these tensions within the system. Please pause the video, take these to be your masses, and understand that there's a coefficient of friction of 0.15 on this surface between the block and the surface. These are hanging frictions. The pulleys are frictionless and the pulleys are massless, and the cords are massless, which of course means that the mass of those relative to the blocks is extremely insignificant, can be totally disregarded. Here's my cartoonish rendition of how to approach these problems, probably inspired by the recent physics doodles. Two parts to this. First, find a, lowercase a, the acceleration, then focus on one mass within the system. By finding a, you are summarizing what the whole system is doing and how all parts of the system are acting in unison. So the reason you're getting that acceleration is it gives you an overall sense of what the system is doing. And then you're going to focus on one part of the system, and then you can examine internal forces. You can't really examine internal forces until you look at one part of the system, but here's where things break down, and I've been listening really closely over the years and really closely the last few days. What people don't realize is in both of these, you are applying A equals F net over M. A equals F net over M. This is how we do it. You're going to keep writing down A equals F net over M, but what you need to realize is that can apply to the entire system. You can look at A equals F net for the entire system. You can say A equals F net for just this one mass, just this mass, these two masses. You can just keep writing it down and you'll actually have different net forces and different masses, but everything will have the same acceleration. Okay, what I just said, I said a little differently than I have in the past, so I want you to maybe pause and rewind and listen to the last like 30 seconds again. We are applying F net over M. The gears imply a mechanical utility about that. Like that's what we do. Here I go. I'm going to solve this thing. Sorry about the faded PDF scan here, but my first step is I'm going to get F net over M. Then I'm going to focus on the 10 kilogram mass. Again, I'm going to use F net over M. Then I'm going to focus on the 20 kilogram mass. And again, I'm going to use F net over M. But there's going to be different net forces in each situation. So here we go. I'm going to explain this part quickly and don't get lost in the math. I'm just going to do F net over M over and over again. So here's the acceleration of the whole system. I can see that the system has this 150 Newton force driving it. That's the most important force in the system, arguably. There's also a frictional force here that's impeding things. These tensions are internal to the system, so we're not going to worry about them. If you do want to worry about them, okay, fine. It's pulling up here. It's pulling in the positive direction of the system here, but then this one is pulling in the negative direction of the system. Those are identical tensions. Those will cancel out. This tension here, pulling in the positive direction of the system. This tension here, pulling in the negative direction of the system. Those are both equal. They'll cancel out. Here we have this weight that's impeding the system as well. So I have 150, which is this weight, minus the frictional force, mu times the normal force, which equals to the weight of the 20 kilogram block, minus 100 divided by my total mass. There is my acceleration of the entire system. I can now write F net over M for the 10 kilogram block. I'm now going to look at just the 10 kilogram block because that'll give me insight into what this tension is. It's time to dig in and analyze that particular one. So the acceleration is F net over M. The net force we can write an expression for, but we're talking about the 10 kilogram mass. Oh, by the way, I know the acceleration. It's positive 0.44 because it's in this positive system direction. Ft1, I don't know what that is. That's the first tension, minus the weight. Yes, this has a weight. Again, I'm focusing on just this mass, just the 10 kilogram mass. Do the math. divided by the mass of 10, solve for the equation with 10, 104.4 newtons is that tension. You can check that out. Do the math and you'll see that if you do tension minus weight for this block, you get 0.44 as the acceleration. Now I shift my attention to the 20 kilogram block, F net over m. Tension minus the friction minus the other tension. Look at this. Look back up here. Tension here minus the friction minus this other tension. Side note, tangent, I just kept trying to solve this problem over and over again. I was forgetting about that left tension. I don't know what came over me, but I kept forgetting that. I kept getting 39. So the acceleration, again, I'm using F net over m, but it's a different mass and a different net force. Still the same relationship, because anytime anything is accelerating, it's got that relationship. So I have tension 2 minus the friction minus force tension original. And so here's my mu times the force normal. Force normal is 200 still the same frictional force on that one particular mass. 20 times that, 8.8, blah, blah, you get 143 newtons. Now there's a trick I can use to test this out. I move down to the 15 kilogram mass. I look at this 15 kilogram mass. I say to myself, all right, well, I should get the same acceleration now that I know that other tension. If I do 150, which is the weight, minus that tension. Why am I doing that? Because this is the positive system direction. It's actually, for this mass, it's down. I know that's counterintuitive, but we just choose positive. I mean, I think it's way more convenient to choose positive as the direction where the main acceleration is occurring. So I just do 150 minus, I'm just doing net force over mass. Oh, look, I get 0.444 meters per second squared. Checks out. In the facet of physics that we're using here is that we're seeing that we can use an equation in multiple ways, even for the same situation. You can reapply that equation to different parts of a situation. This has been Physics from Afar.